So in today's class we'll define what is the x section and y section of a function, and then we'll define when do we say that a function of two variables, so function f of xy, when is that said to be measurable. We did for function of one variable, f of x എന്ന് പറയുന്ന function എപ്പോഴാണ് measurable ആവുന്നത്. So we have seen the conditions for that. Now we'll see for two variables, function of two variables, what is the condition for measurability, and then we'll define what is called a product measure. So that is what we will be doing in this session. So the function f which is defined on x cross y, so that is a function of two variables. So we have the function f of xy. Now by x section of f we mean, so that is denoted by fx, function defined on y, and it is defined by fx of y equal to f of xy. So we are fixing the x value, so x is fixed and fx of y will be equal to f of xy where y belongs to y. So therefore if f is a function from x cross y to minus infinity to infinity, then fx will be basically a function from y to the interval minus infinity to infinity. So that can be that can take the values infinity or minus infinity. Now by y section we mean, so fy is defined as, now we will be fixing y, and fy at x will be f of xy for all x belongs to x. So that will be function again from, so the domain will be x, and so fy will be a function from x to the interval minus infinity to infinity. So that is what we mean by the x section and y section of a function. Now let us look at the condition for function f of xy to be measurable. So again that is similar to the condition we have for function of one variable. So now we have the product measurable space x cross y and s cross j. So consider this product measurable space, and f is a function defined on the domain x cross y. Now we say that it is measurable if for all alpha belongs to R. Again the conditions are similar. So the inverse images, the set of all xy such that f of x greater than alpha, that must be s cross j measurable. So this must belong to s cross j, then we say that the function f is measurable. നമ്മൾ പറഞ്ഞ പോലെ inverse images, again 4 similar conditions ഉണ്ട്. So we can have f of xy greater than alpha, f of xy greater than or equal to alpha, f of xy less than alpha, f of xy less than or equal to alpha. So if function satisfies any of these 4 conditions, then function is said to be measurable on the space x cross s cross j. Now let us look at a theorem. So this is similar to what we have done in the case of sets. So if E belongs to s cross j, we have seen that Ex will belong to j and Ey will belong to s. The same way here, if f is s cross j measurable function, അങ്ങനെയാണെങ്കിൽ fx will be, so fx will be a function defined on the space y, so fx will be j measurable, and fy is a function defined on the space x, and fy will be s measurable. So for this we will use the previous theorem. So we have seen that if E belongs to s cross j, അങ്ങനെയാണെങ്കിൽ Ex will be contained in j, that means Ex will be measurable set on the sigma algebra j, അതുപോലെ Ey will be contained in s. So Ey is a measurable set on the sigma algebra s. For that way, okay, we are given f is an s cross j measurable function, so we'll show that fx is j measurable and fy is s measurable. Now, so we are given that f is s cross j measurable. So consider an alpha belongs to R. I will define E as the set of all xy belongs to x cross y such that f of x is greater than alpha. അപ്പോൾ നമ്മൾ ഈ റിസൾട്ടാണ് അപ്ലൈ ചെയ്യാൻ പോകുന്നത്, ഈ വെച്ചിട്ടുള്ള റിസൾട്ട്. സോ ഫോർ ദാറ്റ് ഐ വിൽ ഡിഫൈൻ ദ സെറ്റ് ഇ ടു ബി ദിസ് വേ. ഇനി എഫ് എന്ന് പറയുന്ന ഫംഗ്ഷൻ എസ് ക്രോസ് ജെ മെഷറബിൾ ആയതുകൊണ്ട് സോ ഇ വിൽ ബിലോങ് ടു എസ് ക്രോസ് ജെ. സോ ദിസ് ഇസ് നമ്മൾ മെഷറബിലിറ്റിയുടെ ഫംഗ്ഷൻ മെഷറബിൾ ആവാനുള്ള കണ്ടീഷൻ ഇതാണ്. എഫ് ഓഫ് എക്സ് വൈ മെഷറബിൾ ആണെങ്കിൽ ഇറ്റ് വിൽ സാറ്റിസ്ഫൈ ദിസ് കണ്ടീഷൻ. സോ ദിസ് വിൽ ബിലോങ് ടു എസ് ക്രോസ് ജെ. So therefore E will belong to S cross J. If E belongs to S cross J, then Ex will be contained in J. So Ex will be J measurable set and Ey will be an S measurable set by the previous theorem. So F S cross J measurable ayadonde E belongs to S cross J. So Ex is J measurable. So we will have Ex belongs to J for all x. Now by definition Ex will be set of all y belongs to y such that xy belongs to E. Now if xy belongs to E, that means we will have f of xy greater than alpha. So this will be equal to set of all y belongs to y such that xy belongs to E means f of xy is greater than alpha. Now if you have a fixed x and y belongs to y, but here x is fixed and y belongs to y, അങ്ങനെയാണെങ്കിൽ by the definition of x section of x, so fx of y എന്ന് പറയുന്നത് that will be equal to f of xy. But here we have a fixed x and y assumes all the values in capital Y. So therefore f of xy will be equal to fxy. So this will be equal to set of all y belongs to y such that fx y greater than alpha. ഇനി Ex J measurable ആണെന്ന് അറിയാം. So therefore this will belong to J. Now J is a sigma algebra. അപ്പോൾ this is in the form set of all x such that f of x greater than alpha ഫോമിലുള്ള ഒരു സെറ്റാണ്. So this belongs to your sigma algebra. That means the function f is measurable. അപ്പോൾ വൺ വേരിയബിൾ ഫംഗ്ഷൻ്റെ മെഷറബിലിറ്റിയുടെ കണ്ടീഷനാണിത്. സോ set of all y belongs to y such that fx of y greater than alpha, this belongs to J. So that means this function fx must be J measurable. So fx is a measurable function on y, and same way we can say that Ex measurable ആണ്. Ex belongs to J. So Ex is measurable. Same way we have Ey belongs to S. Ey belongs to S എടുക്കുമ്പോൾ again we will have set of all x belongs to x such that fy is greater than alpha. So again that belongs to S. That way we can conclude that the function fy is also measurable. So if f is s cross j measurable, then we can say that the x section is j measurable and y section is s measurable. So that is the proof of the theorem. Now we'll look at what is the x section and y section of a characteristic function. We need to show that if v is contained in x cross y, then chi v of x, so that is x section of the characteristic function chi v is same as chi of the x section of the set vx. So this is a characteristic function of the set vx and chi v of y. So y section of this function is same as chi of vy. So this is a characteristic function of the y section of v. Now we will do this using the definition of x section of a function. So നമ്മൾ fx of y is defined as f of xy for all y belongs to y. So x is fixed and y varies. So chi x section of chi v എന്ന് പറയുന്നത് that will be equal to chi v of xy where, so this is for all y belongs to y. Now by definition of chi v, so it will take the value 1 if the points belong to the set V. So it will take the value 1 if xy belongs to V, and it will take the value 0 if xy does not belong to V. So this will be equal to 1 for all y belongs to y such that xy belongs to V. For condition this is equivalent to 1 for all y belongs to y such that xy belongs to V, and again this will be 0 for all y belongs to y such that xy does not belong to V. This means that means it is 1 for all y belongs to y such that xy belongs to V. So this means y belongs to Vx. So for all y belongs to y where xy belongs to V എന്ന് പറഞ്ഞാൽ that will be all values belonging to Vx. So this is all y belongs to Vx. So this will be equivalent to x fix ചെയ്യുമ്പോൾ this will be equivalent to y belongs to Vx, and it will be 0 for all y does not belong to Vx. Now by the definition of again characteristic function, so it will take the value 1 when y is in the set Vx, and it takes a value 0 outside the set Vx. So this is the characteristic function for the set Vx. Vx in the characteristic function ആയിരിക്കും ഇത്. So this will be equal to chi Vx of y. So that way we can say that the x section of chi v is same as characteristic function of the set Vx. So similarly it can be shown that start with the y section the definition you say that we can show that the result will hold in the case of y section also. Next we have a problem. So we will show that if f is s measurable and g is j measurable. So we have two functions f and g such that f is s measurable and g is j measurable, then we will prove that the product is s cross j measurable. So that f is s measurable and g is j measurable. Now for proving fg is s cross j measurable, so for that let us define a function f star on x cross y by f star of xy equal to f of x. We are given that f s measurable ആണെന്ന് തന്നിട്ടുണ്ട്. So we will show that this f star is s cross j measurable. Okay. So for that f star s cross j measurable ആവണമെങ്കിൽ we need to show that a set of this form, set of all xy such that f star of x greater than alpha. So this is a condition for measurability. So if this belongs to s cross j, then we can say that this set is this function f star is measurable. So we will start by defining f star of xy equal to fx. So fx define chedu. So consider the set of all xy such that f star of xy is greater than alpha. Now f star is equal to f of x. So this will be equal to set of all xy such that fx greater than alpha. So this is collection of all points xy such that fx is greater than alpha. In fx എന്ന് പറയുന്നത് that will be a function of variable x alone. അപ്പോൾ it is independent of y. So this set is equivalent to the Cartesian product set of all x such that fx greater than alpha cross y. So this set will be equivalent to, this is collection of all xy satisfying this condition fx greater than alpha. So y can take any value in the set capital Y. So this will be equivalent to Cartesian product of set of all x such that fx greater than alpha cross y. and now we know that this belongs to S and this belongs to J, so this will belong to S cross J. This will be true for all alpha belongs to R, so that will give us F star is S cross J measurable. So this is S cross J measurable function. Similarly we will define G star of xy to be equal to G of xy. Again we will consider set xy such that G star of xy is greater than alpha. അപ്പോൾ G star of xy എന്ന് പറയുന്നത് G of y greater than alpha വരും. So that can be written as x cross set of all y such that gy greater than alpha എന്ന് വരും. ഇനി G J measurable ആണ് തന്നിട്ടുണ്ട്. So again similar way we can show that G star is also S cross J measurable. So we will get G star is also S cross J measurable ആണെന്ന് കിട്ടും. ഇനി on any measurable space if you have two functions, S cross J യിലെ രണ്ട് measurable functions ആണ് F സ്റ്റാറും G സ്റ്റാറും. We know by the property of measurable function, so product of two measurable functions is measurable. So therefore on S cross G F star and G star are measurable, so their product also must be measurable. So Fg by our construction now Fg will be equal to F star G star അങ്ങനെയാണ് നമ്മൾ ഡിഫൈൻ ചെയ്തത്. So F into G will be same as F star G star. So F star G star will be S cross J measurable. So we started with F and G belongs to S and J respectively. അപ്പോൾ അതിൻ്റെ പ്രോഡക്റ്റ് എന്ന് പറയുന്നത് F star G ആണ്, which is S cross J measurable. So therefore this will prove that Fg is S cross J measurable. Now let us define what is a product measure. So the product measure or the definition of product measure follows from this particular theorem. So we will define what is product measure using this, and now നമ്മൾ double integrals define ചെയ്യുമ്പോൾ the order can be changed. So the order of integration can be changed. So first we'll look at the case of characteristic function. So when you have a double integral involving characteristic function, we can actually show using this theorem that the order can be interchanged. So we'll look at the theorem. So the proof is not included, so we will just look at the statement of the theorem. Consider two measure spaces. So we have the measure space X script S and the measure is mu, and then Y script J and the measure on the space is R. So let them be two sigma finite measure spaces. Define for all V belongs to S cross J, define phi x as R of Vx and phi y is defined as mu of Vy. As we have seen, Vx will be a function defined on the set Y. The corresponding measure y യിലെ measure r ആയിരിക്കും വരുന്നത്. So therefore phi x will be defined as r of Vx, and അതുപോലെ Vy എന്ന് പറയുന്നത് that will be set on the space x. x ലെ സെറ്റിൻ്റെ measures respective measures mu ആണ്. So psi of y is defined as mu of Vy. So we have the functions phi of x is equal to r of Vx and psi of y equal to mu of Vy. So then the theorem states that if you have two functions defined in this manner, അങ്ങനെയാണെങ്കിൽ phi will be an S measurable function and psi is J measurable, and integral phi d mu will be equal to integral psi dr. So using this we will now define, അപ്പോൾ we have this result. ഈ റിസൾട്ട് ഉപയോഗിച്ച് we will define the product measure, or we will define product measure എന്താണെന്ന് ഡിഫൈൻ ചെയ്യും. അതുപോലെ ക്യാരക്ടറിസ്റ്റിക് ഫംഗ്ഷന് നമുക്ക് ഓർഡർ ഓഫ് ഇൻ്റഗ്രേഷൻ ഇൻ്റർചേഞ്ച് ചെയ്യാമെന്നുള്ള റിസൾട്ട്. സോ വി ഹാവ് integral over x phi d mu equal to integral over y xi dr. Ni by the property of characteristic function, so if you have v belongs to s cross j, the already നമ്മൾ കണ്ടു characteristic function the x section that will be equal to the characteristic function of x section of the set v, and again chi v of y will be equal to chi vy. So now consider integral over x chi v of y d mu. So integral consider ചെയ്യുക by the property of characteristic function chi v of y will be equal to chi vy. Now by the definition of integrals of characteristic function the integral എന്ന് പറയുന്നത്, so that will be 1 into mu of vy വരും, will be equal to mu of vy. So mu of vy can be expressed as integral over x chi v of y d mu. അപ്പോൾ mu of vy നെ നമുക്ക് characteristic functionന്റെ ടേംസിൽ represent ചെയ്യാൻ പറ്റും. Now similarly when you find integral over y chi v x dr, so this will be equal to integral over y chi v x നോട് equal ആയിരിക്കും dr. Now by the integral definition of integral of a characteristic function, again this will be equal to 1 into r of vx ആയിരിക്കും. So we will get this integral to be equal to r of vx. Ni by the previous theorem integral over x phi d mu will be equal to integral over y psi dr. Phi was defined as phi of x എന്ന് പറയുന്നത് that will be r of vx, and psi of y was defined as mu of vy ആയിട്ടാണ് നമ്മൾ തിയറത്തിൽ ഡിഫൈൻ ചെയ്തിരിക്കുന്നത്. So if this is phi and psi, we will have this condition integral over x phi d mu will be equal to integral over y psi dr. ഇനി ഇവിടെ ഫൈയുടെയും സൈയുടെയും വാല്യൂസ് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക. സോ ദിസ് വിൽ ബി ഇൻറ്റഗ്രൽ ഓവർ എക്സ് ആർ വി എക്സ് ഡി മ്യൂ ഈക്വൽ ടു ഇൻറ്റഗ്രൽ ഓവർ വൈ ആർ വി വൈ ഡി ആർ വരും. നൗ ആർ ആൻഡ് മ്യൂ in terms of the characteristic function. So the first integral this will become integral over x d mu into r of vx in the value substitute here. So that will be integral over y chi v of x dr varum. So this will be the value of r of vx in the value another, and again here mu of vy under mu of vy can be written as integral over x chi v of y d mu. So this becomes integral over x d mu integral y chi v of x dr, and integral over y dr integral over x chi v of x d mu. Now നമുക്ക് chi v of x നെ so by chi v of x we mean that will be equal to x section നമ്മൾ define ചെയ്ത്, so that will be equal to chi of xy for all y belongs to y. Now if you look at this integral that is for all y belongs to y. So on this particular range, that means for all y belongs to y, chi v of x നെ നമുക്ക് chi v of xy എന്ന് റീപ്ലേസ് ചെയ്യാം. So chi v of x will be equal to this for all y belongs to y. Similarly ഈ ഇൻ്റഗ്രലിൻ്റെ കേസിൽ y സെക്ഷൻ ആണ് വരുന്നത്. So chi v of y is defined as, so that will be chi v of xy for all x belongs to x. അപ്പോൾ this functions can be replaced by chi v of xy x സെക്ഷൻ്റെ പ്രോപ്പർട്ടി ഉപയോഗിച്ച്. So this will be equal to chi v of xy. അതുപോലെ y സെക്ഷൻ്റെ പ്രോപ്പർട്ടി ഉപയോഗിച്ച് this will be equal to chi v of xy. So the integral reduced to the form, the integral can be rewritten as integral over x d mu into integral over y chi v of xy dr വരും equal to integral over y dr chi v of xy d mu. So we can see that the order is interchanged here. So here the first integral with respect to y ആണ്, then with respect to x, and here you have x, and here with respect to y. So therefore we can see that the order of integration can be interchanged in the case of characteristic function. So now we will give a proper definition for the product measure. So we have the measure spaces, x script is mu and y script j r. So both are sigma finite measure spaces, and for any v belongs to s cross j, we have this result. ഇപ്പോൾ നമ്മൾ തിയറത്തിൽ പറഞ്ഞതനുസരിച്ച് integral over x phi of x d mu equal to integral over y psi of y dr, where phi and psi are defined this way: r of vx and psi of y is mu of vy. Then from the integral, these two integrals will be equal. Integral phi d mu will be equal to integral psi dr. Now this common value is defined as, so both the integrals will be equal, and this common value is defined as mu cross r of v. So this value is defined as a product measure of a set v belongs to s cross j. So mu cross r of v is integral over x r of vx d mu, അല്ലെങ്കിൽ integral over y mu of vy dr. So this is defined as the product measure.